Hello, I would like to welcome you to our second lecture in 3N03. We'll discuss today some of the basic, I would call circuit theories and basic network theories that we use very often in analyzing circuits. These are all must-know techniques and approaches for analyzing different type of electrical circuits. So we'll start by discussing Ohm's law, Kirchhoff voltage and current laws. We'll talk about mesh current analysis, and then we'll move to the superposition theorem. Ohm's law states that there is a relationship between the current flowing through a resistor and the voltage across it. And this relationship, as can be seen here, is that the voltage is equal to the current multiplied by the resistance value. So V is equal to IR, or I is equal to V over R. And this relationship, by the way, applies only for linear resistors. There's something called nonlinear resistor. But for now, I assume that all the resistances that we deal with in this course are linear unless otherwise mentioned. So you can remember the relationship between V, I, and R through this triangle here. So V over R will give you I multiplied by R will give you V, and V over I will give you R. And for any resistance in this course, the current is flowing from the positive terminal to the negative terminal. So as you can see here, this is the positive terminal, this is the negative terminal. Current inside the resistor flows from the positive one to the negative one. And this is very consistent with what was mentioned before, that the electric field is pointing from the higher potential to the lower potential, and the electric field is really pushing the positive charge in its direction, and this is as well be the direction of the flow of the current in this case. Now, the origin of this law in electromagnetics is the expression we mentioned in the class before, which relates the conductivity and the electric field. So the J is equal to sigma E. If you integrate J over the cross section, J will give you the current, and if you integrate the electric field, see the work done by the electric field, this will give you the voltage. And then each one of these two integrals will give you some other constants, and then you end up with some relationship that V and I are related together. So I is equal to V over R here in this case. Okay, so this really comes again from electromagnetics, and most of the structures, actual physical structures, we can analyze them using electromagnetic laws to determine the relationship between V and I. Okay, so let's start to take a look at one example here. We have actually two different circuits. This circuit here, this one has a current source, and this current is flowing through two resistors in series, 10 ohm and 20 ohm. And the other circuit, it's a voltage source, it's a battery, and there are two resistors in parallel, 10 ohm and 20 ohm. Now, the current source may not be familiar to some of you, but a current source simply supplies the same current, and what is variable here in this case is the voltage across it. So the voltage V across the current source can be anything, but it will always supply the same current regardless. So here this one will supply a current of 5 ampere in this circuit, and the voltage across it will be changing according to the other components in the circuit. While a voltage source like this one, it supplies the same voltage, so 5 volts, while the current being drawn from it, here is the one that changes based on the other components of the circuit. So now we'll consider each one of them, and we'll try to apply Ohm's law to determine the voltages and currents everywhere in these two circuits. Now, when we consider the first one, the one with the current source, because this current is 5 ampere and this is all one loop, so the same current flowing here is the current flowing here is the current flowing here. It looks like one loop here, so it's the same current everywhere. So the voltage drop across the 10 ohm, remember the current is flowing this way, so this is positive than this one, so the voltage drop across the 10 ohm is simply, according to Ohm's law, is equal to 10 ohm multiplied by 5 amperes. So 5 by 10, this will give us 50 volts. The voltage drop across this 20 ohm resistor, again the current is flowing this way, so this terminal is more positive than this terminal, so the voltage across it, which we'll call V2, is nothing but 20 multiplied by 5 amperes. So 5 by 20 amperes will give us 100 volts. And as you will see later from Kirchhoff voltage law, the sum of these two voltages, the 50 volts plus 100 volts, must be equal to the voltage across the current source, which is equal to 150 volts in this case. Now we move to the second example, which we had. We have here a 5 volts battery, and there are two resistors in parallel. Notice that the 5 volts simply is between this point and this point. So there is a difference in potential between this point and this point, which 5 volts. So it is the same potential difference across the first resistor and across the second resistor. So in that case, we can calculate the current going through each one of them individually. So the current flowing here, and of course we have to take into account the polarity of this voltage. This side here is positive than this one. Okay, so the polarity of the voltage of the current is simply to flow from here to here, from the positive potential to the negative potential, or from the higher voltage to the lower voltage. So here this current is simply equal to the 5 volts divided by the 10 ohm according to Ampere's law. The current flowing here in this 20 ohm resistor is simply equal to the 5 volts divided by the 20 ohm. So the first one is 5 over 10, it's going to be 0.5 amperes. The second one is 5 over 20, so it's 0.25 amperes. And as we'll see later from Kirchhoff's current law, the current flowing into this node is equal to the currents flowing out from that node. So the current I, the total current drawn from the battery, is equal to I1 plus I2. So it's equal to 0.5 plus 0.25, or the answer is simply 0.75 amperes here in this case. Actually, all currents are in amperes, all resistors are in ohms. Now, one of the most useful source or laws that we use very often in circuit analysis is Kirchhoff's current law. It's very simple, simply saying that the current flowing into any node is equal to the sum of the currents flowing out from that node. And this law has very strong analogy with water flow in pipes, because if you have some water flow in some pipe, then the current or the water flowing into that node must be equal to the water flowing out from that node in terms of cubic feet per second, or whatever units used in this case. So here in this case, in this circuit shown here, I can simply say that IAB is equal to IBC plus IBD. One current flowing in is equal to the two currents flowing out. And at this node D, I can apply the same law. I can simply say that the sum of the two currents flowing in, IBD plus IBC, is equal to the one current flowing out, which is IAB. But this equation, this second equation, which is written at junction D, is really identical to the one written at junction B. And in general, if we have n nodes, then you have, or n junctions, then the number of independent equations, the number of junctions minus 1. Here in this case, we have only two junctions, junction B and junction D. And as a result, there is only one independent equation that can be written using Kirchhoff's current law. Okay, as an example, let's take a look at this circuit. We have here a number of nodes in this circuit. We would like to write Kirchhoff's current law for this shown circuit. So when you take a look at this circuit, you have to first determine how many nodes do you have. We have one node where these two branches meet. We have a second node here where these three branches meet, and we have a fourth node. This one point is just one node. Okay, it's just one node because there is no element. So these are all effectively one point. And in many electric circuit, we simply take this one as our ground. We say we're gonna arbitrarily give it a zero voltage. We just call this one our zero voltage. Remember that all voltage differences are relative. So you're only measuring the voltage difference between 2 points. So you can pick any point that you want in your circuit and you call it ground. You say, I'm gonna call this one ground, and everything is gonna be relative to this one. So in this circuit that we have three nodes. So we have only two independent Kirchhoff current law equations that can be written. The first one, we can write it here, is that I1, the current flowing in, is equal to I3 plus I2, is equal to the two currents flowing out. And this other node, we can simply say that the current flowing in, which is I2, is equal to the two currents flowing out, I5 plus I4. At this the third node, of course, we can write one more equation, but this equation will be independent of the equation that we written here and here. We have three terminals or three nodes here in this case. Then we have only two independent equations that can be written. So as I said in the previous slide, we had only three nodes, and we have two independent equations. And as I mentioned, they are I1 is equal to I2 plus I3, and I2 is equal to I4 plus I5. Notice here that we have five unknown currents, but we have only two equations. So these equations are not sufficient to solve for the currents everywhere, and we have to take into account other equations which will be characterized by the Kirchhoff voltage law. Okay, Kirchhoff voltage law is simply saying that the sum of the voltages around any loop in a circuit in one direction must be equal to 0. For example, we have, let's take, in this circuit that we have here, we have one loop, we have a second loop, and then we have a third loop. We have three loops, two small ones, and we have one big loop, the one that really encloses both of them. So we can try to write Kirchhoff voltage law in first, say, for this first loop. Remember that the current is flowing in this direction. The current IEB is flowing this direction, so it implies this polarity here of the voltage drop. While the current IBD is assumed to be flowing as shown here in this direction. So in this case, it implies this polarity for the voltage drop across the 3 ohm resistor. Then if you write the Kirchhoff voltage law, is going to be 6 volts, these 6 volts minus 2 IAB. Remember this drop, it has to be minus, it's of opposite polarity to the 6 volts. So 6 volts minus 2 multiplied by IEB minus 3 multiplied by IBD, this is equal to 0. So the sum of all voltages in one direction must be equal to 0. And this makes sense because we have here a battery, and this battery will create some voltage drops. So around this loop, this whole sum must be equal to 0. The same we can do exactly for the other loop. So in this loop here, we have a battery which is 4 volts. Remember, this current is flowing in this direction, so this is the polarity here of the voltage drop across the resistor. The other current IBC is flowing in this direction, so this implies this polarity here across this resistor, positive, negative. So by the same way, we can simply say that 4 volts, and this one here will add this drop in the same direction as the 4 volts. So 4 volts plus 3 IBD minus 4 IBC is equal to 0. Okay, you can see negative, positive, while this one here is positive, negative. So these two came up with positive sign, while this one was a negative sign. Of course, you can write it also for the outer loop. So you can simply say that 4 plus 6 minus 2 IAB, and this one here will be minus 4 IBC is equal to 0. Negative, positive, negative, positive, positive, negative, positive, negative. So this is why the last two were given with a negative sign. Now, where does this come from in electromagnetics? Well, it comes actually from expression for the electric field. There is a law that says that if you have an electrostatic field, the integral of the electrostatic field over a closed loop must be equal to 0, or the work done by the electric field over a closed loop must be equal to 0. And we agreed that the E dot dl over any length is the work done by the electric field, or simply the potential. So this equation is simply saying that the voltage difference or the potential difference around a closed loop must give you 0, any closed loop. Of course, this one here applies for the case where we have a very low frequency. If you go to very high frequency, we end up with a phenomenon called radiation, and radiation will change all this. So there is an implicit assumption here that this one here applies for relatively low frequency. If you go beyond to radiation area, things little change, but we are not going to be addressing that here in this course. We assume that the frequency is sufficiently low enough for Kirchhoff voltage law and Kirchhoff current laws to apply. Mesh current analysis tries to combine both Kirchhoff voltage law and Kirchhoff current law. And the idea in this analysis is very simple. Here we have two main loops, the left loop and the right loop. Of course, you can write as well for the external loop, but the expression you write for the external loop will be dependent on these two. So it's not going to give you any more information. What you do, you assign one current per loop, and say in the clockwise direction or in the counterclockwise direction. Usually they take them in the clockwise direction. It's really a choice that we make. Let's make them in the clockwise direction. It does not really matter. So if we assume here there is a current flowing called I1, there is a current flowing called I2. Now in the 3 ohm resistor, the current flowing the 3 ohm resistor is simply I1 minus I2, because I1 is flowing from top to bottom while I2 is flowing from bottom to top. So the opposite one another. And then we write Kirchhoff voltage law for every loop, and then we solve for the currents in this loop. So for the first loop we have 6 volts minus 2I1 minus 3I1 plus 3I2 is equal to 0. So this will give us this first equation. This equation is nothing but Kirchhoff voltage law written for this first loop. And remember again that the currents flowing in the 3 ohm is I1 from top to bottom and the I2 from bottom to top. So you can actually say it is I1 minus I2 multiplying the 3 ohm. So we wrote Kirchhoff voltage law for the first one. We can repeat exactly the same for the second one. We have here 4 volts. I2 is flowing in this direction, and because it's flowing in this direction, it's creating a voltage drop this way. So we can simply say that 4 volts minus 3I2 plus 3I1, because it's flowing in the opposite direction, minus 4I2. Remember, the voltage drop across this one will have this polarity. So it's again is opposing the 4 volts. This is equal to 0. So what we did here, we wrote 2 equations. One equation for the first loop, a second equation for the second loop. And you can put them in matrix form. So here you have minus 3I1 minus 2I1. This will give you minus 5I1. You have 3I2, so it can be written this way. This 6 can be moved to the other side. So this is going to be equal to minus 6. We do the same here. We move 4 to the other side, becomes minus 4. You have 3I1 minus 7I2. So the first equation is minus 5I1 plus 3I2 is equal to minus 6. The second equation is 3I1 minus 7I2 is equal to minus 4. And we solve these 2 equations by inverting this matrix. And when you invert this matrix and you multiply by minus 6 and minus 4, you get this answer for the 2 currents. So I1 is equal to 2.077, I2 is equal to 1.461. And just remember, the current flowing in the resistor 3 ohm disjoint resistance is equal to I1 minus I2. So it's equal to 2.077 minus 4.7, but 1 minus 1 minus 1.462 flowing from top to bottom. Okay? So this is really what mesh current analysis is. You assign to every loop a current, and the current going through any joint resistances is simply the difference between these 2 currents, and then write one equation for every loop. Okay, let's consider this example here. We'd like to solve for the currents in this circuit using the mesh current method. And here I have a typo in this example here, because the value of this resistor is actually 5 ohm, is not 50 ohm. So we take this one into account when we start to write our equations. This structure is very similar to the one we solved earlier. We have two loops, a first loop and then a second loop. This one is 100 volts, this is 20 ohm, this is 4 ohm, this is 10 ohm, this is 5 ohm here. We assume that there is a current flowing in the first loop I1, there's a current flowing in the second loop I2. And of course the current going through the 5 ohm resistor is equal to I1 minus I2. I1 is flowing from top to bottom, I2 is flowing from the bottom node to the top node. Now we write the Kirchhoff voltage law for these two nodes. Here we have 100 is equal to 20I1 minus 5I1 plus 5I2. This is the first equation. And then for the second loop, we don't have any voltage source. So we can simply say, we can actually put the polarity here for this voltage drop here. We can put the polarity here for this voltage drop. And for this one as well, we have this polarity here. It's going to be plus and minus. Okay, so we can write the same equation here. We can simply say that 10I2 coming from this one plus 4I2 coming from this one plus 5I2 coming from this one minus 5I1 coming from I1 flowing through the 5 ohm is equal to 0. And then by solving these two equations, the equation resulting from this loop and the equation resulting from this loop, we end up with a system of equations we can solve for the currents. So here we have these two equations, 100 minus 20I1 minus 5I1 plus 5I2 is equal to 0. Or for the second one, we have 5I1 minus 5I2 minus 4I2 minus 10I2 is equal to 0. We assemble all the I1 components here. This will give us minus 25 and this one will give us 5. 100 will be moved to the other side to become minus 100. We assemble all the I2 components here, 10, 4 and 5 give us minus 19. The I1 is multiplied by 5 here and this is equal to 0. This is one matrix. We can try to invert it, and if you invert it, you end up with a solution that I1 is 4.22 and I2 is equal to 1.11. And of course, the current going through the 5 ohm resistor is simply equal to I1 minus I2. So it's 4.22 minus 1.11, it is 3.11 pointing downward. So by doing so, I now know the currents in all the resistances of this circuit.